Good evening, everyone. Let us carry forward our discussion and enter into the last week of this course. Okay. So I hope you had a good exam today and everyone have scored well. Okay. So let us also finish the course, our discussion, and the last week's content. So in this week, we will be mainly studying two more special types of concrete. Basically, one is the polymer concrete. Okay, so how it is different from conventional concrete, and secondly we will go to a concrete which is having a lot of potential. Okay, because it can be cast in a controlled environment. Okay, so that is nothing but the precast concrete. Okay, so we will be going basically about these two these two special types of concrete, and we will see their properties, how the curing, how other phenomena are done, and what are their characteristics, behavior, and how is it how is it special. Okay, so how it is different from conventional concrete. So yeah, so let us start our discussion. So let us study what is polymer concrete. Okay, so how do we use polymers in concrete? So basically, as we know, the general definition of concrete is that the aggregates. Okay, so concrete basically consisted of coarse and fine aggregate, water, and the binder. Okay, the cement. So the idea is that the binder, okay, binds the aggregates and keeps together. Okay, and makes it a uniform. Material. Okay, a homogeneous material, which we assume basically. So the question is, can we bind the aggregates using any other constituent other than hydrated cement? Okay, so basically what we use is the gel. Okay, the cement gel. But are there any option, okay, other than the hydrated cement gel, which can be used for binding the aggregates? Okay, the answer is yes, and that is we can use polymers and asphalt. Okay, there are some of the examples of such binders. Okay, so basically we will be restricting our discussion to polymers. Okay, studying of asphalt is beyond the scope of this course. Okay, so we will be confined to basically the polymer concrete. So let us see. So in concrete, polymers are basically used in three types. Okay, so there are three forms in which polymers can be used. One is the simple polymer concrete, which is very obvious. Second is the PIC, or the polymer impregnated concrete, and third is the LMC, that is latex modified concrete. Okay, so what is PC? That is polymer concrete. So that is, polymer is used directly as the binder. Okay, to replace Portland cement in gluing aggregates together. So there is no use of any binder. Okay, and even if cement is used, that is used as a filler, not as a binder. So that is completely replaced by polymer. So it is polymer concrete. The second form is polymer that is applied as an impregnating agent to penetrate a Portland cement concrete member for enhancing its properties. Okay, so here actually the binder is PCC, that is Portland cement concrete, but polymer has been used as an impregnating agent. Okay, so it has been used as an impregnating agent to to improvise its properties. Okay, to better its properties. Okay, and third form is that polymer can be used as an admixture. Okay, so it can be used as an admixture, and those polymers which can be used as an admixture basically, or SCC. Okay, so they are categorized in the bracket of LMC. Okay, so that is latex modified or polymer modified concrete, and it is mainly because in this category of polymers, latex is mainly used. Okay, so that is why it is also known as latex modified concrete. So now let us go in detail about each of them. Okay, so in polymer impregnated concrete and latex modified concrete, okay, so the polymer acts together with the cement binder because it is completely not substituted. Okay, so there is mainly the cement binder is there, and those are there for enhancing its properties. Okay, however, in polymer concrete PC, as we just studied, the polymer alone acts as the binder because it completely gets replaced by the binder. Okay, so the binder is completely replaced by the polymer concrete, so it alone acts as the binder. So the basic idea of polymer concrete is to replace the hydration of cement, okay, in conventional concrete with polymerization reaction for obtaining a reasonably strong and compact end product. So our basic idea of using polymer concrete is replacing cement hydration with polymerization. Okay, so let us now see how the two processes, that is cement hydration and polymerization reaction, okay, are how are they different from each other. Like let us see what is the difference, what are its uniqueness, and how both both has its own advantages and disadvantages. Okay, so if we see in case of PCC, that is hydrated gel, hydrated cement, and it's in if we see in portlet cement concrete, which allows cement hydration. So here the binder is hydrated cement. Okay. However, in case of polymer concrete, that is PC. So let us substitute Portland cement concrete as PCC and polymer concrete as PC. Okay. So in PCC, the binder is cement, hydrated cement. Okay. However, in case of PC, the binder is a polymer. In PCC, it involves hydration because there is cement. Okay, but in case of PC, it involves polymerization because there is no cement. In PCC, water is a reactant because hydration occurs in presence of water. But in case of PC, water is eliminated during the process because it is not a cement. Okay. So apart from that, PCC, as we all know, it is a slow process. Okay, because 98% of strength is formed after 28 days. However, PC is a rapid process. That is, it completes within a day or two. Okay. Apart from that, PCC does not require any external heat. Okay, but PC sometimes require heat. Okay. In case of PCC, products and their composition change with time. Okay, so because with hydration new products are being formed. Okay, but in case of this PC, products do not change with time, so they are constant. And in case of PCC, hydrated products may contain voids and cracks. Generally they contain both of them. Okay, but in case of PC, the end product has very minimum voids. Okay, so it has a lot of advantages. Okay, so a polymer is defined as an organic material. Okay. So if we ask basically now what is a polymer, so it is basically defined as an organic material which is composed of a series of repeated chemical units. Okay. So the single unit can be defined as a monomer, and all those units are linked together in a chemical way. Okay, chemically. So that is basically a polymer. It is an organic material which is composed of a series of repeated chemical units called monomers. Okay. So monomer, again, if we define, it is an organic molecular species that is capable of combining, okay, chemically with molecules of the same species or with other species. Okay, thereby forming a polymeric material of higher molecular weight. Okay, so these are basically all organic molecular species capable of combining chemically, okay, with molecules of same or different species, and thereby forming a polymeric material of higher molecular weight. Okay, and the chemical process through which the conversion from monomer to polymer takes place is called polymerization. So what is polymerization? It is nothing but a chemical process which is used for converting monomer to polymer. Okay, as you can see here, so this is a monomer. Okay, uh, which is a molecule having CH double bond CH2 and CH2, and there is a benzene ring. So this is a monomer. After polymerization, it becomes a polymeric material having a high molecular weight. Okay. So during the polymerization process, the monomer molecules chemically attach themselves to one another for forming chains that are very long and flexible and become entangled. Okay. So the two types of polymerization processes, okay, which are basically present. One is addition polymerization, and second is condensation polymerization. So as the name suggests, addition is basically polymers where the monomer molecules are same, okay, belong to the same species. They simply combine and add to each other. Okay, whereas in case of condensation polymerization, the monomer species are of the monomer molecules are of different basically different species. Okay, so as you can see, the this one the monomer molecules are of different species, so therefore it involves reaction between two monomer molecules which are usually chemically different, thereby forming a new chemical bond between the two. Okay, and the molecular formula of the repeating unit is different from that of the monomer. Okay, because there is combination of two monomer molecules of different species. So therefore the molecular formula of the repeating unit, that is the condensed monomer, okay, after monomer produced after condensation, is generally different from the like the molecule formula for the polymer is different from that of the individual monomers. Okay, so polymerization is typically a chain reaction. The polymerization, it is initiated by the action of a free radical on a monomer molecule, which may lead to polymer chains. Okay, consisting of thousands of monomer molecules. Okay, so basically, it is created by action of a free radical on a monomer molecule. Okay, and they result in formation of polymer chains. Okay, which consists of thousands of monomer molecules. And when subjected to heat, okay, or in the presence of a promoter, these free radicals are formed by the decomposition of a relatively unstable material called an initiator or a catalyst. Okay, example of one of the initiator is benzoyl peroxide. So these free radicals, okay, they are formed through the decomposition of a relatively unstable material when subjected to a heat. Okay, and this heat can be referred to as a promoter, and the free radicals are the decomposition of relatively unstable material, which are known as initiator or a catalyst. Okay, an example of an initiator is a benzoyl peroxide. So this diagram, okay, so although it is not properly clear, but as you can see, so the reactions are occurring, okay, due to the help with the help of an initiator. Okay, and thereby this monomer is being attacked, and through this there are chains of thousands of monomers formed and resulting it into a polymer. Okay, so this is the process of polymerization. Okay, so the rate of polymerization depends on the concentration of initiator and temperature. Okay? So more will be the initiator, more will be the rate of polymerization, and also the promoter, that is temperature. So both is directly proportional to the rate of polymerization. The end products like polystyrene, polymethyl methacrylate, etc., have required tensile, compressive, and flexural strengths and are resistant to chemicals. Okay? So these are the end products: polystyrene, polymethyl methacrylate, etc. Okay, and they are having tensile, compressive, and flexural strengths of a significant value, acceptable value, and are resistant to chemicals. So basically, these are the polymers formed after polymerization. Okay. Now let us go through each of the types of polymer, that is PC, PIC, and LMC. Okay, polymer concrete, polymer impregnated concrete, and latex modified concrete. So first let us study polymer concrete. So it is produced using the two-step procedure given below. The first step is pre-mixing a two-part polymer system, which is composed of monomers or pre-polymers with hardeners, that is cross-linking agent. And the second step is the mixture is added to aggregates to produce a hardened plastic material, okay, with aggregate as filler. Okay, so firstly pre-mixing a two-part polymer system, which is composing of monomers or pre-polymers, okay, using cross-linking agent, and then the mixture which is obtained is added to the aggregates for producing a hardened plastic material, okay, where the aggregate acts as a filler. Okay, which is similar in conventional concrete also. In general, the aggregates used in polymer concrete should be dry, okay, because the polymerization process does not occur on wet surfaces. So this is one important criteria. So as dry as possible, the aggregate should be present, because polymerization process occurs only on dry surfaces, not on wet surfaces. Okay. Some commonly used monomers, okay, or pre-polymers of PC, okay, are methyl methacrylate, that is MMA, polyester prepolymer styrene, and epoxide prepolymer. Okay, so these are some of the commonly used monomers or prepolymers. Okay, MMA, methyl methacrylate, polyester prepolymer styrene, and epoxide prepolymer. Okay, other components used include catalyst, plasticizer, fire retardant, and fibers. So these are some of the other components also, okay, which can be used. uh, they include catalyst, plasticizer, fire retardant, and fibers. Okay, the composites do not contain a hydrated cement phase, although Portland cement can be used as a filler. Okay, so the composites, they basically do not contain hydrated cement because it is completely substituted by polymer. Okay, and Portland cement can be, although Portland cement can be used, okay, but not as a hydrated cement, but as a filler. Okay, so polymer concrete is mixed, placed, and consolidated in a manner similar to conventional concrete. Okay, so polymer concrete Polymer concrete is mixed, placed, and consolidated in a manner similar to conventional concrete. Okay, with some harsh mixtures, external vibration is required. Okay, the coefficients of thermal expansion of polymer materials are significantly higher than the conventional concrete. Okay, the modulus of elasticity of polymer concrete may be significantly lower than that of conventional concrete, especially at higher temperatures. So this may be one of the problems. Okay, the modulus of elasticity, that is the E value, in case of polymer concrete may be significantly low as compared to the conventional concrete, and that is particularly specific at higher temperatures. So now comes the question about what are the advantages and disadvantages of PC. Okay, so that is polymer concrete. Okay, so if we go into a little bit more detail, we will find that the advantages of PC are as follows. It has high tensile and flexural strengths. It has excellent adhesion. It has good resistance to attack by chemicals. It has very low water absorption. It has high water resistance. It has good resistance to abrasion, and it has good freeze thaw stability. Okay, so these are the advantages of PC. Okay, now let us see what are the disadvantages of PC. So there are some of like few fundamental disadvantages, one of them being a very high price. Okay, so that is the reason why, although it is having such advantages, but still its usability, okay, and its economy and its feasibility is a little bit question, okay, which needs to be further researched upon. Okay, so apart from the high price, there are other disadvantages, a few of them, such as low Young modulus, as we just studied, particularly at higher temperatures, high creep values, sensitivity to high temperature, and poor bonding with conventional concrete. So these are some of the disadvantages of polymer concrete. Okay, so let us see what are the applications of polymer concrete. So basically they are used in patch repair works in highways. Okay, they can be used for fast curing, high strength patching of structures. The polymer mortars have been used in a variety of repairs where only thin sections, that is patches and overlays, are required. Okay, and polymer concrete is especially suitable for areas subjected to chemical attack. Okay, so these are some of the areas, okay, where polymer concrete can be used. Okay, so now let us go to the second form of concrete, which is second type of polymer concrete, which is the polymer impregnated concrete. Okay, where it impregnated to hydrated cement. Okay, so that is PIC, polymer impregnated concrete. So if we see what is PIC, let us see. So basically produced, okay, by impregnating a monomer and catalyst, okay, into a hardened concrete and polymerizing it using steam or infrared heater. Okay, so PIC is basically produced by impregnating a monomer and a catalyst into a hardened concrete and polymerizing it using steam or infrared heater. Okay, so what is the procedure basically? So precasting, it is basically you first hard Portland cement concrete is hardened. Okay, so we have to precast hardened Portland cement concrete, then we have to dry the conventional precast concrete. Okay, then we have to displace the air from the open pores, then the saturated we have to saturate the open pore structure by diffusion of low viscosity monomers, okay, or a pre-polymer monomer mixture, and then what is required is in situ polymerization with heating. So everything has to be made in the control environment, okay, like precast, then drying, displacing the air, and then diffusion of low viscosity monomer or pre-polymer monomer mixture, and inside, that is at the original place, we have to start the process of polymerization through heating. Okay, so if you see here, it is a pictorial schematic representation of how the PIC is done. Okay, how it is developed. So if you see here, so polymer impregnated concrete is made by impregnating a monomer and catalyst into a hardened concrete and polymerizing it using steam or infrared heater. Okay, so basically in a hardened concrete, the PIC is impregnated. Okay, that is the monomer and catalyst is impregnated, and the polymerization is done using steam or infrared heater, that is by heating. Okay, so some commonly used monomers are basically, as we studied just before, some commonly used monomers are MMA, that is methyl methacrylate, styrene, and acrylonitrile. Okay, so PIC usually has low permeability and diffusivity than conventional concrete. Okay, and its applications are basically structural industry floors. Okay, then sewer pipes. Okay, then storage tanks for seawater. Okay, then structural members for desalination plants and distilled water plants and tunnel liners. Okay, so these are some of the applications of PIC. The amount of monomer that can be impregnated into a concrete specimen depends on the total void space. Okay, either through vacuum or thermal drying to remove air and water in pores, the maximum monomer loading can be increased. Okay, so more we can dry the sample and remove air and water in the pores, the maximum monomer loading can be done. Okay, it can be increased. The application of pressure helps in reducing monomer loading time. Okay, so more is the pressure, better is for polymerization, because it reduces monomer loading time. So latex. Now let us go to the third type of polymer induced concrete, which is the latex modified concrete (LMC). Okay. So LMC is produced by adding polymer latex into a Portland cement concrete mixture during the mixing process. Okay. Both cement hydration and polymer film formation processes occur together. Okay. A co-matrix phase is formed by both cement and polymer film formation processes, because both of them are together present. Okay. So if we see, okay, so the latex modified concrete basically has a three-step process. Okay, which is involved in the formation of polymer film on the cement hydrate. So first step is the polymer particles are uniformly dispersed in the cement paste phase. Okay, in the second step, with the development of the cement gel structure, the polymer particles are gradually confined, okay, in the capillary pores. And third step, okay, with the removal of water during cement hydration, the closed packed polymer particles on the cement hydrates basically coalesce into continuous films or membranes. Okay, so this is how latex modified concrete, okay, is used by through the formation of the polymer film in the cement hydrate. Okay, so the membranes basically bind the cement hydrates together to form a monolithic network. Polymer phase interpenetrates throughout the cement hydrate phase. Such a structure acts as a matrix phase for latex modified mortar and concrete. The aggregates are bound by the matrix phase, okay, to the hardened mortar and concrete. Okay, so this is how the latex modified concrete works basically. Okay, so uh, if we see the LMC, okay, that is basically produced by adding polymer latex into a Portland cement concrete mixture during the mixing process itself. Okay, the polymers, that is the admixtures, which here it has been used as an admixture. So it is used to gauge the cementitious mortar as a whole or as partial replacement of the mixing water. Okay, so the polymer admixtures which can be used which are used for the cementitious mortar. Okay, so they can be substituted fully or partially in terms of the mixing water. Okay, as we all know, polymer does not like water. Okay, so when latex is incorporated in a cementitious mortar, a network of polymer strands formed, okay, interpenetrating the cement matrix basically. Okay, so when basically the latex is incorporated, okay, in the cementitious mortar, a network of polymer strands are formed, okay, interpenetrating the cement matrix. Okay, such mortars afford similar alkaline passivation protection to the steel as conventional cementitious materials do. Okay, so the passivation protection, okay, of the mortars are similar to the steel as done by conventional cementitious material. Okay, so latex can be either natural or man-made. Okay, natural latex come from the rubber trees, and man-made latex is created by the synthetic processes. Okay, so both latex can be used. Okay, man-made as well as natural. Okay, so the most widely used latexes with Portland cement are copolymers of styrene butadiene (SB), 100% acrylic copolymers (PAE), styrene acrylic SA, vinyl acetate ethylene (VAE), and polyvinyl acetate (PVA). So these are some of the most widely used latexes. Okay, in Portland cement. Okay, these latexes comprise organic polymers that are combinations of various monomers such as styrene, acrylic, butadiene, and vinyl acetate. Okay, so the latexes basically are organic polymers which are combinations of various monomers such as styrene, acrylic, butadiene, and vinyl acetate. Okay, the form of latex is usually a dispersion of very small particles of an organic polymer in water. The range of size of particles in latex is from 1500 to 2500 angstrom. That is 0.15 to 0.25 micrometer in diameter. Okay, so this is the range of particles in latex. Okay, the solid content in a latex emulsion is about 50%. Okay, so 50% is the solid content in the latex emulsion. The application of latex in Portland cement concrete requires about 15% of solid content by weight of cement. Hence, about 30% of emulsion by weight of cement has to be used. Okay, so yeah, the solid content is 15% by weight of cement, and therefore 30% of emulsion has to be used for this. Okay, by weight of cement. So this is the latex application process. Okay, so thus 15% of water by weight of cement is brought into concrete. Okay, that is 15 plus 15 equal to 30. Okay, so this is the emulsion that is made, and therefore the water has to be reduced from the free water for concrete mixing, because this 15% of from the free water is taken during the application of latex with this 15%. Okay, totaling into 30. Okay. So reaction of LMC involves two processes basically. One is the cement hydration and second is the latex coalesce. Okay, coalescence. So basically, if we see, uh, so the LMC reaction involves firstly cement hydration, where the chemistry and reaction processes of cement hydration occurs in the same way as in conventional mortar and concrete. Okay, with water being removed from the latex emulsion, the latex particles get closer. Okay, and secondly, what happens is the coalescence of latex. Okay, so with continual water removal, the latex particles can eventually coalesce into a film. Okay, coating the hydrate and aggregate surface with a semi-continuous plastic film. Okay, so these are the these are the processes. Okay, which by which LMC is achieved. Okay. So, as the latex particles coalesce and form a semi-continuous film, moisture can be maintained around the cement particles. Okay, and thereby permitting the cement hydration process to continue and reduce the need for an external wet cure. Okay, this process occurs after the material reaches its initial step. Okay, for many mortar applications, the materials are formulated with some latex so that no external curing is needed, whereas for most concrete applications, the normal curing procedure is 1 day of moist cure followed by air drying for the remaining curing time. Okay, so many mortar applications, in case of many mortar applications, the materials are formulated with some latex so that no external curing is basically needed. And in case of most concrete applications, the normal curing procedure is basically 1 day of moist cure. Okay, followed by air drying for the remaining curing time. Okay, that is for the normal curing casting, concrete casting. Sorry. So for the moist cure of concrete, damp burlap and polyethylene films are typically used. Okay, so this is a type of membrane curing. Okay, so usually surfactants are added to the latex formulation to prevent latex particles from coagulating due to the influence of severe mechanical or chemical conditions. Okay, and these surfactants can bring these surfactants can bring a large number of air voids into LMC due to the nature of the surfactant to foam. Okay, so although it is added for preventing coagulation, but it has a problem that it can bring a large number of air voids into LMC. Okay. So an antifoam agent is added to the latex to control the air content in the Portland cement mix. So for preventing this, an antifoam agent is also added to the latex for controlling the air content in the Portland cement mix. Okay. Latex can influence the properties of mortar or concrete in both the plastic stage as well as the hardened stage. Okay. In the plastic stage, the combined characteristics of latex and antifoam will cause some air to be entrained in the mix. Okay. The entrained air voids act as a lubricant and thus improve the workability of the modified concrete. Okay. One more factor contributing to the improved workability is the dispersing effect of surfactants on the latex combined with the water. Okay. So, uh, these are the main factors which are improving the workability. One is entrained air voids, and second is dispersing effect of surfactants on the latex, okay, which is combined with water. So the setting time of latex modified mixes is usually controlled by the hydration of the Portland cement, okay, and the because main binder phase is the cement hydration, okay. So basically, it is completely dependent on this only hydration of Portland cement, the setting time. The available working time for finishing, however, can be considerably shorter than an unmodified composite. Okay, due to the latex drying and film formation initiated by evaporation of water from the surface of the mix. Although the setting time is related to the cement hydration, but finishing available working time, okay, for finishing is less, okay, because there are new phenomena, okay, such as latex drying and film formation, which is initiated by water evaporation from mixed surface. Okay, so this causes the formation of a crust on the surface which can tear if overfinished. Okay, in the hardened stage, latexes can improve adhesion properties, tension and flexural properties, permeability, and chemical resistance of latex modified mixes. Okay, so these are some of the properties which latexes can improve in hardened stage. Okay? The bond of latex modified mortar to concrete is chemical in nature, thus creating a homogeneous combination of the two materials. Bond tests have demonstrated that ultimate failure is in the parent concrete, okay, but not in overlay, that is LMC, okay. And the poor sealing effects, okay, of latex in a concrete mix results in a major reduction of its permeability to both gases and liquids. Okay, carbonation studies have shown that the addition of latex to concrete significantly reduces the depth of carbonation of the concrete. Okay, uh, chloride permeability is also lower in case of LMC. Okay, so depth of carbonation is also reduced in when latex is added, and chloride permeability is also lower in case of LMC. Okay, so let us see what are its applications basically. So it is mainly used in emergency concreting jobs in mines, tunnels, ceramic tile adhesives, okay, and grouting, okay, swimming pool finishes, okay, and industrial floor toppings, okay, as well as the production of high strength precast products. Okay, so these are mainly the applications of LMC, latex modified concrete. Okay, LMC is the most commonly used repair material, which is especially used for overlays on bridge decks or concrete highways. Okay, so because of its various proper advantages and its significance, it is used mainly in repair as a repair material for bridge overlays, okay, and concrete highways. Okay, so now let us see how we can improve the quality of cover concrete. Okay, that is cover grit. Okay, so if we see, so basically we can classify concrete also into two parts. One is which is present in the cover, that is cover grit, and second interior, okay, with the reinforcements, that is the hard grit. Okay, so if we see why is the cover concrete important, okay, so cover concrete, that is the cover grid, affords the first line of defense for protecting the reinforcing bars, okay, against corrosion. So protection afforded by the cover concrete depends on the actual cover provided and the properties of the cover concrete. Okay, the properties of cover grid and hard grid, okay, are very different. Okay, so how why it is different we will see. Okay, so as you can see in this picture, okay, so this is the black circle, it represents the steel reinforcement, and the white rectangle which surrounding this is the hardgrid, and the gray color square rectangle is the overgrid. Okay, and this is the thickness. Okay, so it is intruded by chloride and carbon dioxide. So why the formwork is important? So the kind of formwork used to cast concrete plays a vital role in determining the properties of covered concrete. Okay, so for determining the properties of covered concrete, the kind of formwork basically cast okay, used to cast concrete plays a very vital role, and it in return will depend make it in return will determine how is it how the how is the actual concrete is resisting the corrosion. Okay, so conventional formworks majorly of plywood and steel are impermeable. Okay, when fresh concrete is vibrated, bleed water moves towards the top and besides of the formwork. That is a normal phenomenon, as we all know. So due to the bleeding, there is increase in the water to cement, that is W by C ratio in concrete in the neighborhood of the impermeable formwork. Okay, this increase leads to increased porosity and permeability, and hence make the structure less durable. Okay, so because of there is increase because of the increase in water cement ratio, okay, in the neighborhood uh, of the impermeable formwork, there is increased porosity and permeability, and that may make the structure less durable. Okay, thus though concrete surfaces produced using impermeable formworks have been plain and smooth, they may not rank very high according to the durability criterion due to weak near surface concrete. So because of the above mentioned causes, okay, although the concrete surfaces produced have been plain and smooth, but they will not rank very high according to the durability criteria. Okay? So, how to enhance the surface properties of concrete? The question is now about that. Okay? So there are various materials. Okay, various materials that can be used for this one, enhancing the surface properties of concrete. Okay, so one of the methods for enhancing is the use of silane. Okay, so what is silane? Basically it is 100% monomeric isobutyl alkyl alkoxysilane. Okay, which is applied to hardened concrete for reducing the ingress of water and soluble salts. Okay, so this is one of the methods. Okay, so the size of silane molecules is similar to that of water, and so it penetrates into capillary cavities. Okay, and it has a size of around 50 to 1000 angstrom. Okay, so in the order of 10 to the power minus 10. Okay, so that is much smaller. Okay, so it can easily occupy the voids in concrete where the absorption occurs. So when applied, the silane adheres to the walls of the pores and reacts with the absorbed water for forming a hydrophobic layer. Okay, so that is they form a water repelling layer. Okay, so since silane is a non-film forming application, okay, the air permeability of the near surface concrete is not significantly altered by its use. Okay, because it is a non-film, like it does not result in any film. Okay, it just makes a hydrophobic layer. Okay, so the silent treatments are not lifelong, however, and need to be reapplied periodically. And it is widely used on bridge structures by local authorities in Europe, USA, and many other countries. And the manufacturers of silane generally recommend a second application 4 hours after the first application. So these are some of the guidelines and requirements which are needed for the use of silane. Now let us go to one more material which is called microsilica. Okay, so microsilica is also known as condensed silica fume. Okay, CSF, and it consists of discrete microspheres of silicon dioxide. Okay, and it has a size of zero point 0.1 to zero point 0.2 picometer. So it is in the range of 10 to the power minus 12. Okay, so compared to the cement, okay, the microsilica has a much greater surface area, and this provides, because of their small size. Okay, so it has a much greater surface area, and this provides a larger surface for reaction during the hydration process. Okay, this when added to a mix aids the formation of a stronger and more durable concrete. It fills the space between the cement and aggregate particles and acts as centers for the formation of a secondary calcium silicate hydrate crystal growth. Okay, so it has two purpose, like it solves two purpose. Firstly, it fills the space between cement and aggregate particles, and secondly, it acts as a center for formation of secondary calcium silicate hydrate crystal. Okay, so it allows the growth of CHS. Okay, secondary CSH crystal. The increased density of the mix reduces the bleed water, therefore, when concrete is being placed, and results in a less porous near surface concrete. The resulting near surface concrete, okay, is less permeable, as less escaping water leaves fewer interconnecting pore systems of smaller size. Okay, while being widely used in Scandinavian countries, microsilica is normally used only in special circumstances in other parts of the world. Okay, so the main problem of it is cost. Okay, the money. So there, although it has very good advantages, but the advantages like the cost outweighs the advantages. Okay, so therefore it is mainly used in Scandinavian countries. Okay, so apart from that, it is only used in special circumstances. Okay, in other places of the world. So that is the second. First was the silence, second was using microsilica. Okay, so these were the materials which could use the which could enhance the surface near surface property. Let us see the third way. Okay, so it is by using CPF liner. Okay, so CPF is nothing but control permeable formwork liner. Okay? So this CPF liner is manufactured in a way that it allows water to escape through it while ensuring that cement particles are retained on its surface, which has the effect of reduced water cement ratio and consequently reduced porosity. Okay, so these are formworks, okay, which are having lines, okay, which allow water but does not allow cement particles to move, like to flow, and therefore the water cement ratio is reduced, and therefore there is a reduced porosity. Okay, because no, like less trapped water will be there, which will generate less amount of voids. Okay, so therefore reduce porosity. This fabric, when mixed to formwork, allows access what air and water, which would normally form blowholes, okay, on the concrete surface to drain away. So this fabric, that is the use of CPF liner, would allow the excess air and water to drain away instead of forming blowholes on the concrete surface, as we all know. The free draining surface of the formwork means that the water cement ratio at the surface is reduced considerably. Okay, obvious, which in turn leads to a surface region with enhanced physical properties. Okay, because the free draining surface of the formwork, okay, is present, so the water cement ratio at the surface is also reduced, okay, considerably as compared to the one which does not have has it, okay, which does not have this facility, and therefore it has an enhanced physical property. Okay, so this is a pictorial representation of the use of CPF liners. Okay, so as you can see here, there is a way. Okay, this is the support, this is the concrete, and in between there is a way through which water and air can pass, but cement particles will get stuck. Okay, so there are various types of CPF liners. Okay, commercially available CPF liners are very expensive, approximately $20 to $25 per square meter, and they are not easily available. Okay, so one study has been carried by GARG, okay, in 2019, and that was conducted at IIT Kanpur, and they had compared the performance of three types of CPF liners. One was commercially manufactured liner, which is JED. Second was gunny and gunny bags, and third was particle board. Okay, so it is found that gunny bag and particle board are readily available on construction sites at a negligible cost, okay, and aligns with goal of green construction. So both of them, 2 and 3, were useful, gunny bags and particle board. So apart from that, you can see here also how the effect of CPF liner, the use of how its use can reduce the water cement ratio, okay, in normal strength concrete. Okay, so apart from that, the because of the water cement ratio reduction, we could see that the pull off strength, okay, in the CPF, in concrete having CPF liner, had increased, okay, tremendously, and there is a decrease in water surface water absorption also. Okay, because of the this one, because the water flows away. Okay, Apart from that, there is because there is reduced porosity, so decrease in charge passed through RCPT is also less. Okay, so there is decrease in charge passed through RCPT because of reduction in porosity, and also there is decrease in chloride ion permeation. Okay, because of the reduction porosity reduction. Okay, and apart from that, as we all just discussed, there is a decrease in blow hole ratio also. Okay, because the water moves away, so there is no holes. Okay, blow holes, so it has reduced tremendously. So from this, okay, so if we conclude based on the CPF liners, the conclusions which we achieve is that the surfaces which were produced by Z ranked has shown maximum improvement. Okay, followed by gunny bag and particle board except for ISAT values. Okay, and though commercially manufactured CPF have ranked highest, that is the jet category, locally available and highly economical material gunny bag has shown a noteworthy improvement in the surface characteristics and can be considered as an alternative to expensive commercially manufactured CPF for various applications. Okay. However, the hardened surface cast against gunny bag has the impression of gunny bag. So this is one of the small problem, because the hardened surface, okay, which was cast against gunny bag, took the shape of gunny bag. Okay, the impression of the gunny bag was pasted there in the surface. The efficiency of permeable formwork liners is increased with the use of high water content. So more is the water, okay, bleeded water. More is the higher water content, more will be the bleeding water, or more will be the bleeding water. More it will be able to pass through the liners. Okay, so the permeable formwork liners efficiency will increase with the use of higher water content. Okay, so if we see permanent formwork, look into permanent formwork, we will see that find that unlike temporary formwork, okay, permanent formwork stays in place, okay, acting as an additional stabilizer, making it an appealing alternative to precast concrete and temporary building methods. Okay, and so it does not have to be made every time. Okay, so it will be permanent, and it will be stabilizer. Okay, it can act as a stabilizer, and it is also appealing. Okay, the process uses hollow panels which are filled with concrete. Okay, and remaining in place, forming a permanent structure. Okay, so there it uses hollow panels, okay, which are filled with concrete, and then it remains in place, forming a permanent structure basically. So it provides extra stability and protects concrete from any type of deterioration. So these are some of the uses, advantages of permanent formwork. So permanent formwork reduces the time and processes required for both commercial and residential builds, because we don't have to make it every time. So it is safer sites for workers also, because there is less chance of any failure or any damage going on. So quicker project turnarounds can be achieved. It will also require reduced labor requirements, and care is needed during, but one of the thing is that care is needed during construction for reducing the risks of hidden defects. Okay, so although it is much more reliable, still there may be some chances of hidden defects present. So utmost care is needed for during construction for reducing the risk of hidden defects. Okay, so here are some of the types of permanent formworks. Okay, one is the profile steel. Okay, so as you can see here. Okay, so this is a type of permanent formwork, profile steel. Second is the steel mesh. Okay, and third is precast concrete panel. Okay, so these are some of the uh, these are some of the uh, this one for permanent formwork. Okay, profile steel, steel mesh, precast concrete panel, etc. So if we now see, okay, what is its use, or the common usage. Okay, let us firstly go for profile steel. So profile steel is composite beam and slab type concrete floors with the formwork spanning between either steel or concrete beams. Okay, they are roof floors within the depth of the permanent works. Okay, supporting members. Okay, and this is the schematic diagram of profile steel. Now let us go to this one, its advantages and disadvantages. So advantages that it has a large span range, as they are light and easy to handle. Its defense supporting steel frame. Okay, there can be easily cut and fitted to awkward shapes. Okay, and sealing between panels is achieved by lapping edges and ends. Okay, So these are some of the advantages. Let us now see the disadvantages. So excess or ripped profiles are difficult, okay, when in position, okay. The exposed steel sheet providing the tensile reinforcement is susceptible to fire damage, and additional reinforcement may be needed in the slab for providing adequate fire resistance, okay. So the this some of the disadvantages are also there, like excess or rip profiles, okay, difficult, and exposed steel sheet providing the tensile reinforcement is susceptible to fire damage, and additional reinforcement may be needed in the slab for providing the adequate fire resistance. So this is all about the profile steel. Now let us see steel mesh, okay. So steel mesh with small opening is similar to large size aggregate size, okay. So this is a mesh, okay, which is having openings which are equivalent to large aggregate sizes. So it is commonly used in construction joints in slabs, deep construction joints, vertical construction joints to walls, okay. And this one, mm, wall and column formwork, okay, for further finishing or rendering, soffit formwork, okay, and curved wall formwork. So various types of formwork are used. It is used in various ways, okay, as various formworks such as construction joint, deep construction, vertical construction, wall column formwork, soffit, and curved wall formwork. Okay. So its advantage is that it is light and easy to handle, okay, and it is easily cut and fitted to awkward shapes by unskilled labor, okay. The pour can be monitored from partially exposed face, okay, and its disadvantage is that it is produces an unformed face, okay, which is acceptable for stop ends like repetitive work to receive further concrete, but must be rendered or faced for a fair finish. So these are some of the issues, okay. So if we see the third category, okay, it is the precast concrete panels, okay. So precast concrete panels up to 200 millimeter wide, reinforced by welded lattices which project into and provide a mechanical linkage with the in situ concrete slab, okay. So this is its utility. So it is a very wide structure, okay. So the formwork is very wide, about 2.4 meter wide. So what are its common usages? One is composite concrete floors spanning between either steel or concrete beams, okay, and composite bridge decks, okay, spanning between either steel or concrete beams, okay. So these are some of the common usages of precast concrete panels, as you can see here. So what are its advantages? So firstly, large areas quickly placed with mechanical handling, okay. So the rate of construction can be very high, okay. Secondly, it has a large span range, okay. And thirdly, it is very compatible. The material is very compatible, so it can be used anywhere and everywhere. And with it also comes certain disadvantages, such as it is relatively heavy and it will require mechanical handling, okay. It compromise reinforcement detailing, okay. And the tolerances of panels and permanent works creep, okay, during positioning, okay. So uh, these are some of the issues, okay, pertaining to this its use, so which need to be addressed upon, okay. So now let us see one more special topic in concrete, or even special concrete, that is compaction, okay. So why it is important and how it affects, okay. So why compaction? As we all know, compaction of concrete, also known as consolidation, is to achieve the highest possible density of the concrete by removing of voids, okay. So vibration has the effect of fluidifying the mortar component of the mix so that internal friction is reduced and packing of coarse aggregate takes place, okay. So it increases the abrasion resistance and general durability of the concrete, decreases the permeability, and helps to minimize its shrinkage and creep characteristics, okay. And it has a direct impact on achieving the specified surface finish, okay. So these are some of the utilities of compaction, okay. So it is basically a two-stage process, okay. The compaction of concrete. Firstly, the aggregate particles are set in motion and the concrete consolidated, okay, to fill the form and give a level top surface, which is also called as liquefaction, so that the water comes up, okay. and second stage is the entrapped air is expelled. So we will see more about this in the coming slides. So this description of the process is true whether compaction is carried out by rodding, tamping and similar manual methods, okay, or when vibration is applied to the concrete. So basically compaction is done by two ways, one is manual and second is by machine. So manual is rodding, tamping, okay, and other similar manual method, and the mechanical way is by vibration using some machine, okay. The latter, that is the mechanical one, okay, so the latter by temporarily liquefying a much larger volume of the concrete, it is just generally much more efficient, okay, than tamping or rodding by hand, and hence is almost universally used. So we generally see machine, okay, compacting, okay, and therefore its uses were quite universal in nature, okay. So basically if we see there are two stages of compaction. So first is the process. In this process, liquefaction of the concrete occurs, which allows it to slump and fill the form. Okay, and it takes around 3 to 5 seconds. Okay, for the first stage to complete. And the second stage, the expulsion of entrapped air is done. Okay, so it generally takes around 7 to 15 seconds. So if we combine both, okay, the liquefaction and expulsion process, so it will take from 10 to 20 seconds, okay, for both stages of the process to get completed, okay. So this is a schematic representation of the concrete compaction in both the stages, as you can see here. So let us see what is the process of compaction. So it is important to understand that compaction is a two-stage process, okay, and to recognize each stage, because with vibration, initial consolidation of the concrete, that is liquefaction, can often be achieved relatively quickly, okay. So from 3 to 5 seconds it can be achieved, but that does not mean that complete compaction has been done, okay? The concrete liquefies and the surface levels, okay, giving the impression that the concrete is compacted, okay, but that is not completely true, okay, because the second stage is still not completed. Entrapped takes a longer time, which is the second stage, because it takes a longer time to rise to the surface. So compaction should therefore be prolonged, okay, until this is accomplished, that is until air bubbles no longer appear on the surface. So compaction, okay, should be done until the time no air bubbles are present on the surface or appearing, or seen on the surface basically, okay. So if you see here, so let us see what is the effect of compaction on on the fresh concrete basically, okay. So let us see what is the compaction effect on the fresh concrete, okay. So type and amount of vibration applied to the concrete should be appropriate, okay. Otherwise defects such as excessive mortar loss and other forms of segregation can be caused, okay. So therefore vibration should be appropriate. It should not be less and it should not be also over, okay. The concrete mixture as supplied to the project needs to be properly proportioned. Concretes lacking fines can be difficult to compact, and even when fully compacted can have a high porosity, okay. So these are some of the issues, okay. Concrete lacking fines can be difficult for compacting, and even when after fully compaction it can have a high porosity, okay. So those with too high fines, particularly if they also have a high slump, may be prone to segregation and excessive bleeding. So both lacking fines is also a problem, because it can be difficult for compacting, and it may have high porosity, and also having high fines is also a problem, because it may result in it may result to segregation, okay? And it can also result for the segregation can also result in excessive bleeding. So uh, there is a trade-off, okay. It should not be too low, and it should also not be too high. So concretes with lower workability, that is stiffer mixes, will require a greater energy input to compact them fully. This may be achieved by using a high energy vibrator or by vibrating the concrete for a longer time. Conversely, more workable mixes will require less energy input, okay, and that is like very much trivial, okay. So it is more, if it is more workable, the energy required is less, but if it is less workable, that is stiff, so energy required will be more, okay. The size and angularity of the coarse aggregate will also affect the effort required to fully compact concrete. The larger the aggregate, the greater the effort required, while angular aggregates will require greater effort from smooth require greater effort than smooth or rounded aggregates. Okay? So you know, more big aggregate on angular aggregate, okay, they will also require more energy as compared to smooth and rounded aggregates. Okay, so now let us see the effect of compaction on hardened concrete. Okay, so why compaction is important? Because if as you can see in this picture, if even there is about 10% of entrapped air, okay, the compressive strength will completely half. Okay, so the compressive strength falls by 15% even if there is entrapped air of as less as 10%. Okay, so that's why the entrapped air is of very nuisance. Okay, it is not good for concrete. It improves that, however, this one the little amount is required, okay, for the freeze and thaw and workability. Okay, but the question is of durability. Okay, so the it improves the durability of concrete. Okay, because of the this one because of the freeze and thaw resistance, so little entrapped air is required. Okay, but excessive vibration can expel amounts of purposely entrained air, which is designed to increase the freeze thaw resistance of hardened concrete. So excessive vibration can even expel that amount of purposely entrained air also. So in this case, durability of concrete may reduce because that freezing thawing resistance will be gone. Okay, if there is too much vibration, over vibration. Okay, so excessive vibration can cause an excessive amount of mortar to collect on the surface, thereby reducing its potential abrasion resistance. Okay, so that is also not a good thing, especially for roadways. Okay, carriageways. And in flat work, a careful balance is therefore required to expel entrapped air without bringing excessive amounts of mortar fines to the surface of the concrete. So we need to we need to expel the entrapped air, but we also don't want to bring the excessive amount of mortar fines to the surface. Okay, so it should not be less, it should not be high, it should be in between. So now let us see what are the effects of over compaction. So over vibration should normally be avoided during the compaction of concrete. If the concrete mix is designed with low workability, over vibration simply consumes extra power of the vibration, resulting in the wastage of energy. Okay. For most of concrete mixes, over vibration creates the problem of segregation, in which the denser aggregates settle to the bottom while the lighter cement paste tends to move upwards, as we just studied. So, if the concrete structure is cast by successive lifts of concrete pour, the upper weaker layer, which is caused due to latence, okay, caused by segregation, forms the potential plane of weakness, leading to possible failure of the concrete structure during operation. Okay, so that this is one of the effect of over compaction. Apart from that, if concrete is placed in a single leaf for roadworks, okay, the resistance to abrasion is poor, as we just discussed, for the latent surface of the carriageway. So this becomes a critical problem to concrete carriageway, since where its surface is constantly subjected to tearing and traction forces, which are created by or exerted by the vehicular traffic. Okay, so because the abrasion resistance is reduced due to the higher finer content in the surface, so it will fail quite easily when subjected to tearing and traction forces from vehicles, okay, due to the vehicular traffic in carriageways. So apart from that, also let us see adverse impacts of overcompaction. So one is the honeycombing. Okay. So overcompaction can cause the aggregates to settle down, thereby washing away cement paste that binds the aggregates together. Okay. So it will result in honeycombing. Second is excessive loading on formwork. Okay. So over vibration can damage the integrity of formwork. Okay. Not only concrete. Okay. The formwork will also damage. So in some cases, especially staircase and water tanks, shuttering is easily worn off. Okay. So we have to use a stiffer mix in that case that sets faster in the areas and by default do not overcompacts. So a lot of care needs to be taken. Okay. And third is the bleeding. When the mass below is plain aggregates, the cement paste out to come out somewhere, they bleed and reach the surface of the structure, causing surface cracks to start off and terminally causing collapse of structure. Okay, so those are some of the issues: bleeding and this honeycombing, excessive loading on formwork. These are all ill effects of overcompaction. So proper care needs to be taken. Apart from that, there is even issue of durability. Okay, honeycombing and such defects on account of over vibration are often covered up using cement mortar or plaster. Okay, so this is a very simple solution. Okay, but it is not a long lasting one. it should be remembered that the durability cannot really be restored, okay, if honeycombing and such defects are present. So therefore care should therefore be exercised in ensuring that such stopgap measures are as plastering to cover up the detect defect are not resorted to. So this may be, just covering a defect can be a short term solution, but the appearance of defect is suggestive of the fact that the quality of the concrete is not good, okay, because the honeycombing has occurred. So it has occurred because of the over compaction. So uh, instead of solving the problem, it's better to not create the problem at the first place, okay. That is why it's called prevention is always better than cure, okay. So now let us see the various types of compaction. Okay, as we just simply discussed. Okay, now we shall go in detail. So basically, there are two types of compaction. One is hand compaction, and second is mechanical compaction. We just discussed. So hand compaction is basically rotting damping, and mechanical is using some kind of vibrators, okay, and vibrating machines and vibrating tables. So there are many factors that should be considered to choose compaction methods, such as reinforcement quantities, spacing, concrete paste consistency, and formwork complexity, okay. So in case of hand compaction method, it is reasonably workable and flowable concrete mixtures that are consolidated by hand employing a rod, okay. Bar should adequately reach the bottom of the formwork, and rod diameter need to compact concrete between reinforcement spacing and formworks. Okay. Concrete is stamped by the rod tool repeatedly to consolidate it. Mixtures with low slump value could be consolidated by hand if superplasticizers are added to increase slump and make the concrete workable, okay. So that is mainly about hand compaction. Now let us go to mechanical compaction. So it is suitable for concrete mixtures with great amount of coarse aggregate of content and low water to cement ratio in heavily reinforced structural elements, okay. Basically there are three types of mechanical compaction method. One is shock or drop table, second is centrifugation, and third is vibration method, okay. So what is shock or drop table? So shock or drop table is used to consolidate extremely stiff. Okay, it is used to consolidate extremely stiff, low slum concrete in making precast units. Okay, so it is mainly shock or drop table is used for low slump. Okay, stiffer concretes. In case of centrifugation, it is employed for compacting moderate to high slump mixtures. Okay, so lesser stiff mixtures in constructing poles, pipes, and piles. Okay, so these are used in the centrifugation compaction method is used in those cases. And the vibration method, okay, so vibration method, here the vibration basically, sorry, so here the vibration basically helps in minimizing the internal friction by randomizing the concrete mixture, okay. Vibration rearranges the cement and aggregate particles in concrete, okay. This helps concrete in achieving the closed configuration, and number of vibrations per minute, that is VPM, or vibrations per second hertz, are used to express vibration, okay. So if you see, this is an example of internal vibrator, okay. So it consists essentially of a poker, as you can see, housing an eccentric shaft driven through a flexible drive from a motor. Poker is immersed in concrete and thus applies, as you can see, this poker. So it is immersed in concrete and thus applies approximately harmonic forces to it. An internal vibrator immersed in fresh concrete generates rapidly recurring circular compression waves. Okay, so that is his mechanism. So immersion vibrator can vibrate up to a frequency of 12,000 revolutions per minute. Okay, so it is recommended to keep the vibration between 3,000 rpm to 6,000 rpm and have an acceleration of 4g to 10g. Okay, the poker is easily moved from place to place and is applied at 0.5 to 1 meter or 3 to 2 to 3 feet. Okay, centers for 5 to 30 seconds depending on the consistency of the mix, okay. But with some mixes it can even go up to 2 minutes, okay, because it may be required. To obtain an adequate radius of action, an internal vibrator must operate at a very high vibration intensity, okay, and gradual withdrawal. That is why it has to work in 3,000 to 6,000 rpm, okay, having a vibration and to have a high vibration intensity. Gradual withdrawal of the poker at the rate of about 80 millimeter per second, 3 uh, you know inches per second, okay, is recommended for this one is recommended so that the hole left by the vibrator closes fully without any air being trapped. So we have to use it carefully, and also while removing it, okay, after use, it has to be very slow so that the hole generated by the vibrator, okay, is closed completely without any air being trapped, okay. So pokers are made in sizes down to 20 mm diameter, so that the size of the poker is can be as low as 20 mm, that is 2 centimeters, so that they can be used even with heavily reinforced concrete and relatively inaccessible sections. Okay, the concrete shall never be poured in layers thicker than 600 millimeter or 10 times the diameter of poker. Okay, otherwise its effect will not be very substantial. Okay? It will not be an efficient method. The length of the time that the vibrator employed at the same station is based on concrete workability, force of the vibrator, and the nature of the element that is being compacted. Okay. So that is all about the internal vibrator. Now let us go to formwork. Okay, formwork vibrators. So they are also called as shuttering vibrators. Okay, where the vibrators are clamped externally at some specific points on the formwork. Okay, so they generally vibrate the formwork. Okay, so position of these points decided on the thickness and depth of the concrete uh, inside. Okay, inside the formwork. So thickness and depth. Okay, so both of this matter. Like both of them are used for determining the position. Compaction time or vibrating time in the formwork vibrator is 1 minute to 2 minutes. Okay, it can vibrate at a speed of 9,000 cycles per minute. The formwork should be rigid, okay, and watertight to withstand vibration. Minimum form acceleration of 1 to 3 g, 9.8 to 30 meter per second square, is required for fluid to plastic mixtures when the form is filled with concrete. Okay, and the corresponding acceleration for the empty form is 5 to 10 g. Okay, so that is 49 to 98 meter per second square. Okay, so uh, you know uh, when the form is empty, okay, so it can be used at 5 to 10 g. Okay, and when the minimum, okay, and when it is filled with plastic and fluid mixtures, okay, and uh, like concrete is filled in the form, so it has to be minimum acceleration has to be 1 to 3 g. So this is the example of form vibrator. As you can see here, the form is in the form, the vibration occurs, and that is dispersed, okay, through the concrete medium. Okay, and the vibration is traveling through the concrete medium, as you can see, in a curved manner. So suitable frequency depends on the size and design of the forms. Large forms usually need high frequency form vibrators, okay, to obtain the required event distribution. Type and design of the form usually are more significant in the selection of lower high frequency form vibrators than is the type of concrete to be compacted in the form. Okay, so for form vibrator, the form is more important than the concrete. Okay, so and this is the principle of form vibrator. So the vibration gets propagated through the concrete medium. Okay, so, the form vibration of very stiff mixes may require a combination of high amplitudes and relatively low frequencies. Depending on specific conditions, vibration frequencies between 3000 and 12,000 vibration per minute, 50 and 200 Hz are suitable for form vibration. High frequency form vibration results in a better surface appearance than does form vibration at lower frequency. Okay? So high frequency form vibration results in better surface appearance. Okay, but that might not be that much useful, okay, in case of very stiff mixture. Okay, so there is a trade-off we have to take into account that. Okay, but in case of surface appearance, high frequency is better than lower. Okay, so that is all about form vibration. Now let us come to table vibration, the one which we generally use in the lab, which we also use in our lab. Okay, so that is basically the table vibration. Okay? So it is used for harsh and stiff concrete mixes, and it is a laboratory method. So as you can see here, it is also mentioned. So it is basically a laboratory method because it can be used in situ, okay, in practical applications. Okay? So it is rigidly built steel vibrating table mounted on flexible springs. Concrete vibrating table has a frequency of 50 to 100 Hz at an acceleration of 4G to 7G. Okay, so precast industries to make precast elements use a vibratory table to vibrate the concrete. So it can be used in precast industries. Okay, it is comparatively large amplitudes are needed for efficient and rapid consolidation. So it mainly requires large amplitudes. Okay. So as per research done by Stray in 1960, placement resulted in a product of higher strength and density. Okay. And as per Davies, okay, in 1951, for a very stiff consistency, okay, uh, a circular vibratory motion of the table in a vertical plane produced 10% higher concrete strength than did a horizontal circular vibratory motion, and decrease of 10 to 15% in strength was obtained with vertically directed vibrations as compared with vertical circular vibrations. So these were some of the outcomes of research done, okay, on this table vibration mechanisms. So apart from that, there is surface vibrator. Okay. So surface vibrators are also called as an external vibrators. Okay, because it is used externally on the surface. Beneficial to these slabs having depth up to 10 inches or 250 mm. Surface vibrators are used for the precast slabs and retaining walls. Frequency range of 3000 to 6000 vibration per minute, that is 50 to 100 hertz, and accelerations of 5 to 10 G, that is 49 to 98 meter per second square, are customary. So they are used generally, and this is the principle of surface vibrator. Here also, like the formwork vibrator, the vibration is given on the surface and it propagates through the concrete medium in a curve way, okay, in a parabolic way, where the parabola is upside. So upside parabola way, the propagation of waves, the vibration uh, is happening through the concrete medium, and this is the principle of surface vibrator. So the compaction effort depends mainly on the dynamic stresses generated in the concrete and can be calculated according to a study done by Walls in 1960. So the compaction effort is a function of static load, amplitude, frequency, rate of travel. Okay, and experience has shown that for the same acceleration, the high amplitude, low frequency combination is preferably uh, it is preferable basically over low amplitude, high frequency, okay, combination. So in surface vibrator, for a constant acceleration, high amplitude low frequency is better, combination is better than low amplitude high frequency. Okay. So now let us see the results of improper vibrations of concrete. Okay. So it has been proven that voids occupy about 5 to 8% of total volume in freshly mixed concrete. Okay. So if it reaches 10%, it will, as we studied, the compressive strength will decrease by 50%. Okay. So that is why it is very important. If concrete is not vibrated properly, the voids and air bubbles make the concrete porous. Okay. Uh, which in turn makes concrete prone to segregation and bleeding. So if it is not properly vibrated, voids and air bubbles make the concrete porous, and it will in turn this will in turn make the concrete prone to segregation as well as bleeding. Accurate vibration is required to concrete in order to attain the design strength. Okay, and these are the results of the improper vibration of concrete. One is honeycombing, second sand streaks, coal joints, excessive amount of entrapped air voids that most of the times called bug holes, subsidence cracking, placement lines. Okay, so as you can see in this picture, it is an example of honeycomb, okay, in concrete due to poor compaction or vibration. And here, as you can see, these are examples of coal joints due to poor compaction of concrete. Okay, so the layers are getting different, okay, because of one layer getting stiffer before the placement of the other layer. Okay, so now let us go to the one more special type of concrete which you mentioned, that is the precast concrete. Okay, so as you can see, these are the specimens of precast panels and beams. Okay, as you can see here. So this is a casting area. Okay, so as you can see, these are the casting yard. The sleepers are these are sleepers in the casting yard, and they are heading out from the casting yard, okay, for transportation, and it is done using a crane. Okay, as you can see here. So these are the beams, okay, which have been prepared using the precast concrete methodology, and they have removed some unfinished area so that it can be assembled and fabricated at the time of at the time of placing it in the original structure. Okay, at the time of fabrication. So some areas unfinished, okay, so that it can be connected to other structural members, okay. So similarly here you can see some slabs and beams are there which are having hollow, okay, which are having hollow, hollow area, okay, which are hollow in between, having some hollow, various hollow shapes, okay. And so that here various things can be impregnated, okay. And various members can be introduced, okay. So in order to increase the efficiency and quality, okay. So as you can see, these precast members are used in these buildings, okay, construction of these buildings. And here this is a high rise building where the precast concrete is being used, okay, in the panels. So they are being carried using the tower crane, as you can see here, okay. So yeah, so this way the construction can be done very quickly. And as we discussed, so some area has been left unfinished so that it can be fabricated, proper fabrication can be done, okay. And at the time of assembling, no problem is there, okay, no shortage of space is there. So basically there are six steps in precast construction, okay. In the plan there is the stage of productions, curing and storage, okay. And in the segment of logistics there is transportation, and in the side there is lastly installation and finishing, okay. So basically if we see how the curing is done in precast concrete, so let us start from steam curing. So curing of concrete in water vapor at atmospheric or high pressure is basically steam curing. So curing done using water vapor is the steam curing, okay. So at atmospheric pressure the enclosure temperatures are usually between 40 and 70 degrees centigrade, okay. So the concrete is subjected to water vapor having a temperature of 40 to 70 degrees centigrade, okay. So it is used where early strain gain is needed and where heat is required for hydration, such as in cold weather, okay. In pre-stressing and precast plants, steam at atmospheric pressure provides high early strengths, enabling rapid demolding and reuse of forms, okay. So as you can see, the curing regime, steam curing regime, so there is about 4 hours of delay period. After that there is a heating period of around 2 hours. Then there is the maximum temperature period of around 15 hours, and then again cooling back to the ambient temperature cooling period for about 2 hours, okay. So as you can see, steam curing at atmospheric pressure. So here the prefabricated elements, that is the precast concrete, are usually stored in a chamber and steam is applied. However, specimens are reported to have slightly higher drying shrinkage and moisture movement, okay. So this is one of the problems which need to be researched upon. So this is an practical example of the regime, okay. As you can see, so the rate of heating is 20 degrees centigrade per hour, and similar is the rate of cooling, I guess, yeah. So as you can see, initial delay period is 3 to 5 hours, temperature increase period is 2.5 hours, constant temperature period is 6 to 12 hours, and temperature decrease period is 2 hours, as you can see here. And the maximum temperature, okay, for steam curing which is allowed is 71 degree for as per ASHTO, okay. 71 degrees centigrade as per ASHTO and 70 degrees centigrade as per CSA and PCI, okay. These are some standard codes. And the rate of cooling, okay, so it should be less than 22 degree and 15 degrees centigrade, okay, so that there is no extreme there is no extreme stress generated in the concrete which may result in failure, okay, due to brittleness, okay. So it should be less than 22 and 15 degrees centigrade per hour as per AAS and CSA codes, okay. And the normal ambient temperature should be greater than equal to 11 degrees centigrade, okay. So these are some of the guidelines that need to be kept in mind. So the high pressure process, so it requires a specially constructed steel chamber or autoclave. Since the chamber has to be steam tight, a continuous program is not possible, okay, because we have to move and shift and remove items, so it can be steam tight. So therefore, because it is steam tight, so the continuous program is not possible. Except water is kept in the chamber, and control is therefore achieved by regulation of either temperature or pressure alone. Temperatures of 120 degree to 160 degree centigrade are used, okay, are usual basically, and the steam period is comparatively short, okay. So if there is high pressure, then we can go up to 120 160 degrees centigrade, okay. But under atmospheric condition it is not possible, okay, because otherwise the water inside the concrete will itself get evaporated, okay. So that is also known as autoclaving, okay, high pressure in high temperature, steam curing done at high pressure, okay, that is both high pressure plus high temperature. So that is called autoclaving. So pressure vessel type curing chamber is used in this case. The wet steam should be supplied and the pressure is kept higher than the atmospheric pressure. Following characteristics can be obtained, okay. So it can result in high early strength, high durability, reduced drying shrinkage and moisture movement, reduce efflorescence, improve resistance to external sulfates, okay. So these are some of the utilities. And if we see the low pressure continuous process, so it is most suited to mass production. The concrete units are prepared on a conveyor which carries the fill molds or pellets into a long tunnel where the steam curing takes place. In a short high temperature tunnel, doors may be fitted to conserve heat, okay, and in this case the haulage is usually intermittent, okay. The rope or conveyor advancing by the distance of one truck as the doors at each end are open, okay. So if you see the low pressure continuous process, a long tunnel may have a temperature gradient deliberately formed at each end, and in this case doors may be left open without undue loss of heat, okay. The haulage in this case is usually continuous, okay, the movement is continuous, the road is continuous. The heating of curing chambers, basically let us study this. The heat transferred to the surface heats the interior of the unit by conduction through the mold and outer layers of concrete. The method of heating employed should produce the acceleration of strength required for the least expenditure of energy, and all the units should be heated to about the same temperature. In addition to the external heat, the heat generated by chemical action in concrete is expended in heating the concrete to the desired temperature, okay. So if you see the effect of time and temperature, so let us if you see here the plot between percentage of 3-day compressive strength and the maturity, that is the product of temperature time as we studied early. So you can see, okay, so it is after beyond around about 150 to 1500 this one degree centigrade hour, it is greater than 100%, greater than 3-day compressive strength, okay. So that is the utility of steam curing and high pressure, okay, that is autoclaving, okay. And the and if you see here, these are the pictorial representation of steam curing in the left side, as you can see. And this is mainly steam curing done at high pressure, that is autoclaving, okay. And in the right side you can see the steam curing done at atmospheric pressure, okay. So both has its own advantages. And apart from that, we can use the precast concrete for preparation of yeah, we can use precast concrete for preparation of the the uh, the slabs which are used in drains, okay. So that can be the drain precast slabs, okay, that can be constructed in precast, okay. So it has a lot of it has a lot of utility, okay. So basically the use it will result in less requirement of workmanship and skill labor, okay. And secondly, we can adjust the this one by properly making the forms in the lab itself. We can increase the volume of water that can be collected through the drains, okay, the precast drains. And also the this one is also this will also reduce the weight of the precast drains, okay. So it is having two utility, okay. If we reduce the size, okay, upper size is reduced as compared to the lower size, so the weight is reduced. And apart from that, the larger amount of water can be passed through. And also if we can use some type of if we can use some type of special concretes, okay, like foam concrete, okay, or porous concrete. So what will happen, or some self compacting concrete, so what will happen is the pores will be high, so that will result in the water seeping into the ground also. So we are not only dependent on the direct flow, it can also seep underground, okay. So these are some of the usages of making constructing drain precast concrete drains in the lab, okay. So yeah, so this is it has a lot of advantages. Mainly the advantage is we don't require less amount of workmanship and skill labor is required, okay. And the quality of the concrete can be enhanced, okay, because it will be controlled, okay. it will be built in a control environment. So with this, we are going towards the we are going towards the closure of the course. Okay. So basically, in this course, we had 8 modules. Okay. The first and the second module basically had a review of the normal concrete. The third module, there we studied curing cold and hot weather concrete and its important specifications. And fourth order, okay, fourth module, basically we studied the underwater concrete and roller compacted concrete. Okay. In the fifth module, it was mainly about the self-compacting concrete. Okay. The sixth module, we dived into rheology and fiber reinforced concrete. The mixing shotcrete and high strength concrete was studied in the seventh module, and today we talked about polymer concrete, cover concrete improvement, compaction, and precast concrete. Okay. So after going through all of this, there you may have a question in mind that whether we bring recycled materials. Okay, can we bring recycled materials to the mainstream construction? So the answer is definitely yes. Okay, as per IS 456 2000, which is the basic code for design and construction of concrete structure, so it allows the aggregates and sand, okay, not drawn from natural sources to be used in concrete. Okay, but but it has to be taken with the permission of the engineer in charge. But one factor, okay, which has to be kept in mind is that the recycle aggregate, okay, needs to satisfy the natural aggregate requirements, okay, which is not possible. Okay, it is very difficult, and hence the real question is not to replace, okay, but to look at possibility and implications of lowering, okay, it's lowering itself the requirement of aggregate. Okay, so instead of recycling, why don't we think about how to lower the aggregate quantity? Okay, so that we can make some special concrete and grades, and make some special applications of those concrete, thereby lowering the requirement of the actual aggregate. Okay, so then that can be helpful. Okay, that can be much better, that can be a much more better solution. Okay, so basically we try to strike the, like in this course we try to strike a balance between the science involved and the practice and practical consideration. We largely adopted an engineering centered discussion and use codes of practice to emphasize the importance of accepted rules and standard operating procedures. We try to focus on special provisions that will be needed to draw up quality control when using special concretes, either in terms of material, process, properties, and environment. So yeah, so basically we digged into the various special concretes, its behavior, its quality, its specifications, requirements, and what are the conditions which make it special, okay, as compared to conventional concrete. Okay, so that is the all about the complete course. Okay, now let us go to through some of the problems, basically based on this week's course, this week's content, and let us try to solve those. So the first question is, in the context of polymer concrete, consider the following statements. One, mixture of cement and polymer acts as a binder, and two, the end products has maximum voids. Okay, so which is the best alternative among the following? Both are true, both are false. One is true, two is false. One is false, two is true. So as we know, in case of polymer concrete, okay, so the polymer completely substitutes the cement. Okay, so there is no mixture of cement and polymer acting as a binder. So one is false, and the end product has, in case of polymer concrete, the end product has minimum voids. Okay, so it is not having maximum voids. Okay, so two is also false. Okay, so both the statements are false. That is, the fourth option is correct. So as you can see, the fourth option is correct. The second question, in the context of difference between Portland cement concrete PCC and polymer concrete PC, consider the following statements. First statement, water is a reactant in PCC while it is eliminated in PC. And second statement, products and their composition changes with time in PC while remains are largely unchanged in PCC. Choose the best alternative among the following. Both are true, one is true, two is false, one is false, two is true, both are false. Okay. So we all know that in case of Portland cement concrete, water is a reactant, while in case of polymer concrete, the water is eliminated. So one is true. Okay, but if you see the second case here, if you remember polymer concrete, okay, the products and their composition remains constant with time. It does not change. Okay, so it is false. Okay, it is constant only with PCC. Okay, so sorry, it is constant with PC. Okay, So it changes with PCC. Okay, so it changes with PCC. It does not remain unchanged. Okay, so 2 is false. Okay, so 1 is true and 2 is false. So basically second option is correct. Okay, so 1 is true and 2 is false. So let us now go to the third question. In the context of polymer concrete, consider the following information. Three types of aggregates A, B and C are available and they can be used in a polymer concrete. For selecting suitable type of aggregate, an index named wetness index WI is defined as following. WI is equal to weight of aggregate surface moisture by oven dried weight of aggregate into 100. 3. The wetness index of three types of aggregates A, B and C were determined to be 5, 2.5 and 0 respectively. Based on the information available, which type of the aggregate should be used in polymer concrete? A, B, C, any of A, B or C. So if you remember, we found that the surface of aggregate should have should be dry. Okay, so that polymerization can take place, because polymerization does not take place in presence of water. Okay, so it should be as dry as possible. So as per the relation of wetness index, so the aggregate C, which is having 0, okay, value of 0, so it means there is no weight of aggregate weight of aggregate surface moisture, that is no surface moisture is present. So that's why in this type of aggregate full polymerization will take place. Okay, so the type of aggregate that should be used in polymer concrete is C. Okay, so third option is correct. So as you can see, third option is correct. Let us go to fourth question. For which of the following property or properties the polymer concrete is preferred over the normal concrete? High tensile and flexural strength, high Young's modulus, low creep values, good bond with conventional concrete. Okay, so which of the following property the polymer concrete is preferred over normal concrete? So if you remember, polymer concrete improves results in high tensile and flexural strength. Okay, so it is preferred over normal concrete in case of high tensile and flexural strength. Okay, so first option is correct. Apart from that, it results in low Young's modulus, high creep values, and it does not have good bond in conventional concrete. Okay, so all the three are wrong apart from the first one. Okay, so yeah, so high tensile and flexural strength, that is first option is correct. So yeah, high tensile and flexural strength is correct. So fifth question, which of the following is most suited to complete the following sentence? Use of impermeable formwork in reinforced concrete member results in dash. Increment of temperature in cover concrete, reduction of water cement ratio in cover concrete. Okay, increment of water cement ratio in cover concrete and cracking in cover concrete. So use of impermeable formwork in reinforced concrete member will result in increment of water cement ratio in cover concrete. Okay, so the third option is correct. So as you can see, increment of water cement ratio in cover concrete is the correct answer. Sixth question, different formwork are proposed for two RC columns X and Y constructed from the same concrete mix. Column X consists of impermeable steel formwork, while column B consists of CPF liners applied on the surface of concrete. Concrete core were extracted from the surface of both the columns. Okay, and to determine the permeability of the surface concrete, uh, it was permeability of the surface concrete was reported as Px and Py for column X and Y respectively. Based on the information provided, which of the following is correct regarding Px and Py? Okay, so Px would be higher than Py. Okay, Px would be lower than Py. Px would be equal to Py, and it cannot be inferred. Okay, so if because in the case of impermeable steel formwork, the water cannot move. Okay, so that will result in higher water cement ratio, which is resulting in uh, large porosity. Okay, because of the water. Okay, when it gets the water blow the blowhole. Okay, so the blowhole results in higher porosity. Okay, and that will result in high permeability. Okay, so because it is impermeable formwork, Px value will be higher. Okay, and Py will be less because it will be having reduced water cement ratio, so no porosity, like very little porosity, so less permeability. So Px would be higher than Py. Okay, so first option would be correct. So as you can see, Px would be higher than Py. Okay, seventh question. In the context of compaction of concrete, consider the following statements. 1. High amounts of fines cause segregation while compaction. 2. For stiffer concretes, the time of vibration using an internal needle vibrator may be increased. Choose the best alternative among the following. Both are true, one is true, two is false, one is false, two is true, both are false. Okay. So yeah, so in concrete compaction, okay, high amount of as we have studied, low amount, okay, so low amount will result in more this one, more honeycombing, okay, and in case of this one high amount, okay, so that will result in this one, that will result in bleeding, okay, and that will result in segregation because the fines will try to collect itself in the surface, okay, so that is true, one is true. And uh, you know uh, as regards to the second statement, in the case of stiff concrete, okay, for its complete proper compaction, okay, the time of vibration using an internal needle vibrator has to be increased, okay, because it is stiff, okay, more energy is required, and the time of vibration has to be improved, incremented for proper compaction, okay, so both are true, one is also true, two is also true. So the first option is correct. Both the statements are true. So as you can see, both the statements are true. Eighth question. Okay. So which of the following is not a result of the improper vibration of concrete? Honeycombing, coal joints, formation of ITZ, subsidence cracking. Okay. So honeycombing, coal joint, and subsidence cracking all are the byproducts of improper vibration. Okay. So improper compaction is resulting in all these three problems in concrete. Okay. But the ITZ is basically interfacial transition zone. Okay. So that is basically the zone between the mortar and the core aggregate. Okay. So which is the weakest zone. Okay. And that is the weakest area where the failure may take place. Okay. And the pores are connected. Okay. So yeah, so that has nothing to do with vibration, okay, so that will be forming whether or whether we use vibration or whether we don't use vibration, irrespective of whether we are using or not vibration, or whether we are properly or improperly doing vibration, this ITZ will always form, okay, so it is not a result of the improper vibration of concrete. So the third option, that is formation of ITZ, is correct, okay. So yeah, so as you can see, formation of ITZ is the correct option, okay. So with this we have come to the end of the course, okay. So I hope that you had a good time, okay, and you learned something from the course, okay. So yeah, so with this I would like to end, okay. So if you have any doubts, you can ask. Okay, so since you don't have any doubts, so let us end, okay. And I hope that we will in near future we will have a meeting very soon, we will have a discussion on a new topic, okay, in this NPTEL course, okay. So with this I would like to end our course. Have a great day. Thank you.